Well, that's great fun and just about credible enough for the kids to rush up in the interval and peek through the curtains to find out what the guitarist Billy Bob Broccoli's up to. But they are just robots controlled by a computer. And I suppose it would be possible to program it to have them smoking a cigarette or reading a book or whatever it is that real musicians do in the interval. It may seem a very curious way of selling pizzas, but there are over 200 showbiz pizza places opened up in the US. And that means over 200 Duke LaRues. Creative Engineering is the company that designs a range of shows for pizza chains. They make all their characters in a factory in Orlando, Florida. Although the shop floor may look bizarre, it's an ordinary assembly line like any other, and this is the quality control section. This chassis will end up as Fats the gorilla we saw earlier. All the parts are moved by compressed air, electric motors, or solenoids.
We have the coach of the Mississippi Dirt Daubers here after their victorious...
One of their newest and most advanced characters is Uncle Clunk, a TV sports presenter.
Do we got him on the line there, Click?
He's on the line.
Okay, let's pick him up. Hello, Coach Finch.
Well, Pop, this is Coach Finch here.
Yeah, Coach Finch.
Yeah, this is Coach Finch here.
Coach, congratulations on your win last night, Coach.
Just down the road at SeaWorld, animated figures controlled in similar ways are combined with real actors to create an undersea stage show. A domestic microcomputer controls the sequencing of events in the entire show. Lights, slide projectors, and the mechanical bit part actors.
More than looking pretty, it's a little silly. It's coral reef, the coral reef. All the little fishes, they got their wishes. They love that coral reef.
Just 5 minutes down the freeway is Walt Disney World.
Epcot Center covers an area twice the size of the Magic Kingdom. The centerpiece of this international community is the American Adventure.
It's here that the animation of mechanical figures is called animatronics.
A cast of 33 audio animatronic figures, led by Mark Twain and Benjamin Franklin, recreates the drama of 350 years of American history.
Putting the finishing touches to an animatronics tableau for a new exhibit is Wathel Rogers, one of Walt Disney's key animation artists. Today, he uses his traditional talents in 3 dimensions.
What I think we should do, have him hold just a little longer on the seal, and then he can't stand anymore. Take him away from that.
His assistant works at a kind of keyboard that uses a specially designed computer language. He lets them set a start and an end position for a movement, and then automatically fills in everything in between, in a similar way to the laborious in-betweening, as it's called, in hand-drawn cartoons. The final results can be quite spectacular, and often on an enormous scale. How realistic those robots look depends on how many different movements they can do. For example, Fats the gorilla playing the synthesizer has 16 or so, whereas the amazing Uncle Clunk has 32. Today we're looking at output devices controlling movements. They're called actuators. Well, in our dummy here, Steve, we actually have 8 different movements. He can wink each eye, he can wink them both, he can waggle his eyebrows up and down, and he can move his mouth. Oh! Bet you didn't see my mouth move, did you? And we can also program the computer so he does them all in a little sequence and shows off every movement that he's got. There he goes. And they're driven by these devices inside him. How are they controlled, John?
Well, they're controlled by this unit down here, Mac. This takes compressed air coming in here, and these valves, controlled by signals from the computer, send the compressed air up each of these pipes to the actuators. And you can see you're making that actuator move. Now, those actuators work like this. This is just a slightly larger one, but working on the same principle. Air comes in here, and there's a piston. When the air moves in, the piston gets pushed up. And to move the piston back down, you push air in that end, like that. Now, that's a pneumatic actuator, and there's some very similar ones, hydraulic actuators, working exactly the same way, but using liquid instead of air. The hydraulic actuators are good because you can get the position of the piston much more accurately than with the pneumatic ones. There are only really 3 other actuators in common use: an electromagnet, which just attracts that into the centre of the coil, a DC motor, which rotates when you put a voltage across the wires, and this is a stepper motor. When you put a pulse of electricity across these wires, the stepper motor moves around a certain fixed angle.
We'll be looking at all those in more detail a bit later on. Well, those stepper motors can vary in size from quite small ones to very large, and they're often found in industrial applications. On a small farm in the south of England, John Storrs is making early keyboard instruments like spinets, harpsichords and clavichords in kit form. Making the kits means accurately drilling hundreds of holes in some of the keyboard parts. So John has designed his own drill system to do this automatically.
This is a computer-controlled programmable drill which we've constructed. It is controlled on 2 axes of motion by stepper motors. That is, it moves in that direction and in that direction. Stepper motors are small digital DC motors. Because the stepper motor isn't very powerful, we have to gear it down with this timing belt. And as you can see, when the stepper motor shaft moves round, the main shaft moves also. The various elements of the machine slide on ground-mild steel slideways, and there's a rack concealed below that the teeth of a pinion engage in. The problem with stepper motors is that by themselves they don't have any feedback. It's necessary, I've found, with machines of this type, to operate them in a closed-loop mode, where some means or other of telling the computer which controls the motion that steps have actually occurred takes place. And you can see here we have a prototype feedback arrangement, a vane with slots in it, and here we have a small device. It's an opto detector, which consists of an optical emitter and a detector on opposite sides of a slit. And that device is positioned thus. At each time that the motor steps, the slots move around and signals are fed back to the computer. We've done all our own software development. We use Pascal because it's a structured programming language. There's no doubt about it, structured languages are ideal for this type of programming.
Using a structured language, John can define each drilling operation as a single procedure.
An example you saw in the complex hole involving 2 square slots. The hole pattern is defined in the form of a procedure which is repeated in different positions along the piece.
But stepper motors were used in the computer-controlled drill, and they're also used in this buggy. And apart from the corners, we're able to draw quite a reasonable representation of a square. Well, there are 2 stepper motors in this, and this is one here. John, how does a stepper motor work?
We've got a model of something which will illustrate the principles quite clearly. Stepper motor consists of a lot of coils of wire wound on a magnetic material, so that when 2 coils are energized, it attracts the armature between them, rather as a compass needle would be attracted to point north. Now, if these 2 coils are energized instead, then the armature is attracted to those 2. And so you can make the thing rotate by energizing one pair of coils after another. Now, of course, in a real stepper motor, you have a lot more than just 4 coils, but this illustrates the principles quite well. The most important thing is that the stepper motor always moves through a fixed angle, in this case just 90 degrees. Now, you can see on the screen here a representation of what's going on inside the stepper motor and of the coils, and the coils are connected through switches and controlled by bits coming out of the computer. And there's a sequence of bits which switches on the right coils in the right order. Now, as well as connecting this model to the computer, we've got a real stepper motor here. In fact, it's the one out of the buggy. You can see, as we go around, it steps a small amount each time, a very defined amount. Now, I'll just load another program in, and you'll see that we can actually make this stepper motor move as if it were a continuous motor. Now, it goes round, and it looks as if the movement is continuous. But in fact, it's going around in a lot of small steps. But you'll also see the thing's not very powerful, and I can stop it quite easily with my finger.
The reason for that is all these different small coils rather than 1 or 2 very large ones.
That's the reason. That's the reason. Now, if we have a look at the program, you can see it looks very much like BASIC, but there are a few extra words, and in fact we're running a language called Control Basic, which has got a number of extensions to the ordinary version of BASIC. And it says here, make bits 0 and 1 outputs, which tells the computer that bits 0 and 1 of the socket that the device is plugged into are to become outputs so the computer can control that. And then there's a loop here which controls each of the 2 wires in the right sequence to make the motor rotate. And there's a delay, proc wait here, between each of these changes. And proc wait, down here, says repeat until time is greater than 0, which causes virtually no delay at all, and the thing runs flat out. If we change that so that there is a considerable time delay, say 100 units, and then run the program, now with 100 units between each change in the levels of the bits, you can see the stepper motor steps quite slowly. The steps are quite obvious. I'll just change it to another value, this time a delay of 5/100ths of a second. And in that case, you can see we've almost got continuous motion, but in fact made up of a number of small steps.
So the computer can keep a complete track of where that motor is at any particular time.
Yes, it knows exactly that one step, 7.5 degrees.
But the disadvantage, it's got no power. Suppose we want to use it as a DC motor, a powerful motor. How do we know where the position of that is?
Well, yes, well, you have to somehow or other sense where the motor has got to. Now, in a Ferris wheel, like this in a fairground...
Built, no doubt, by Steve once again.
Oh, yes, he's been at it again. This time we have a DC motor here, which drives the whole thing. But if you want to know where the wheel is, then you have to feed information back. And we've got a number of marking points on here. On each strut, we put a reflective strip and a sensor here. So that sensor, connected to the computer, can tell the computer when one of these struts is going past the sensor.
So you'd know when a cage was going past, but you wouldn't know necessarily which one.
No, and you've got to have another set of sensors to mark in some way cage number 1. And in fact, this is cage number 1, or cart number 1. And here we've got another reflective strip and another sensor down here, which is able to determine when that particular cage goes past, so that we know we're at cage 1, after which the other sensor can keep count of those things. Now, at the moment, the computer doesn't know where it is. If you rotate that slowly, it'll suddenly sense when it gets to cage 1, there it goes, and from then on, it can keep control or keep count of the carts as they go past. Now, if I turn the power on, we can make the computer drive that, and of course, we could use the computer to stop the DC motor when a particular cage got to the bottom. So, if I can find the right button to push, there we are, it'll offer me the ability to stop at a particular cage. Now, which one would you like, Mac?
Well, let's say 4.
Stop at cage number 4, right? So if I push it now, it's waiting for number 4 to come up. Has it managed?
And there it is. He's got a big jump, but he's probably back.
Yes, he's a big chap. I think he'll manage. Of course, the problem with that is that you've only got 6 positions which are fed back into the computer. And very often you want to know in a lot more detail exactly where something is. Now, here we've got another piece of equipment which has got sensors on it, 2 potentiometers this time, which enable the computer to know very accurately where those arms are pointing. The 2 potentiometers are, in fact, at this joint here and that joint there. And they can sense the angle through which the arm has turned. Potentiometer is just like a volume control in a radio. And as you rotate it, you can arrange for it to produce a different voltage, which can be fed back into the computer.
So that's an analog input, which is converted digitally in the computer.
Yes, and with a fine resolution, the computer can know exactly how far the thing is rotated around. Over here, we've got some servo motors, which consist of 2 items. One, a DC motor, which is quite a powerful device, and secondly, a potentiometer, which can sense how far the motor has actually turned round.
I'll recognise those servo motors, the sort of things used in model gliders and aeroplanes and racing cars and so on. So you need great precision with them and also a certain amount of power.
Yes, you do. And those work very well indeed if you want to move from one position to another. But very often you want to be able to control the speed at which your motor is moving and not just the position it arrives at. Now, if you want to control the speed of a motor, then you have to change the voltage that you feed into it. Now, computers are digital devices and they feed out digital numbers, not analog voltages. So somehow or other you have to convert those digital quantities into analog voltages. And a device to do that is called a digital to analog converter. The computer feeds digital quantities in and an analog voltage comes out. We've got one in here. The analog voltage is connected to drive that motor. So if I stop that program and run a different one, here I can feed a number into the digital to analog converter, the number 100, and it will produce a voltage which makes the motor rotate at a certain speed. If I feed a different digital number in, try a random number like 42, you'll see we get a different speed for the DC motor. So we've got a powerful DC motor controlled in that way. This unusual chair has been developed by Southampton University for use in seasickness trials by the Institute of Naval Medicine. The chair is moved in 3 axes of rotation by heavy-duty direct current motors. Sensors are fitted to each axis. Feedback from the sensors will allow the system to cope with people of different weight, and the chair can simulate anything from a slight swell to a heavy sea. Dr. David Brown is in charge of the project.
Well, David, why have you decided to use a computer to drive this system?
Well, the chair has 3 large DC motors, each controlled by the computer. This gives us the flexibility of being able to put different types of waveforms in, unlike if we'd used a mechanical cam arrangement, which would be a fixed amplitude, fixed frequency type arrangement. But we also feed back the position loops and the velocity loops to the computer, so we can make a tight control system. Additionally, information coming from the patient in the chair can be fed back to the computer, taken into its memory, and then later stored onto a magnetic disk for the doctor who's running the trials to come back and collect that data.
Lovely. Now, the computer is a digital computer, in fact, and yet, obviously, the human being is moved in a different way, in a sine wave or something like that. How do you generate the sine wave with a digital computer?
The chair's motion is, of course, analog, and it's a continuous motion. We're not a jerky step-type motion. But this is the step waveform here. As you can see, it's more like a staircase arrangement. This comes via the digital to analog converter in the computer, which will, of course, only give discrete levels, as any computer system can. But there are 256 of these discrete levels in one cycle. So the motor isn't sensitive enough to pick up these small steps, so it sees it as a continuous waveform.
Well, this is a 3-colour plotter that can be driven by a micro, even an ordinary home micro. It's quite cheap, and it uses the principles of control we've just been seeing. John Holdsworth, the inventor, and it really has drawn a very nice square there, John. How does it work?
Well, Mac, we've used a design that allows a micro to make the mechanics completely simple. And if you take the lid off, you'll find that there are, in fact, only 2 moving parts. There are 2 drive wheels, rather like the buggy, but in this case, we've used cheap DC motors and the control and checking is done by optical encoder discs.
That one there, yes, I see it. And there's one on the other one as well. But what sort of things can it do?
Well, if we look over here, we've got one that's been plotting some time now. And you can see that under the commands from your computer, it can draw lines, circles, and even characters just by typing in the character codes on the keyboard.
How does it know where it's located?
The position's controlled by dead reckoning from the last time it redated on the edge of the paper. And at the moment, in fact, it's drawing quite smooth circles. And all of these are achieved by the firmware in the microprocessor in this base unit. Periodically, it will go back to the edge of the paper and check its position. In fact, you can see it doing that now.
Oh, yes, there it goes. I see, yes. What sort of uses do you expect it to have?
Anywhere that you're using line graphics on the screen and you wish to have hard copy on paper, business graphics, drawings and designs and so on.
Well, thanks a lot, John. Well, it's clear that this plotter needs to move with a high degree of precision, and the same thing applies to the big clunkers in industry. Well, this is a very powerful industrial robot. It's controlled by 6 motors, and the position of each of those motors is monitored by an optical encoder like this one. And on this crystal disc, thousands of lines are engraved, so the position of each motor can be monitored with a great degree of accuracy. The overall control of those motors is, of course, with a computer. In fact, more than one computer. It's 2 16-bit computers that work together to track exactly where the position of this point is and how to move those motors in combination to move it from one position to another. To program it is really quite straightforward. Instead of having a command language, the commands are a series of buttons on a control panel like this. So if I press one, it will move that way, or it will turn or turn back. So all I have to do is to position the tool where I want it to move to, and that is stored in the quite large memory in this computer, so that when I have to run it again, all I have to do is to touch a button and it will go through the sequence of events that I've programmed into the main memory. Now, it will actually do rather more complicated things than that. I'm going to describe a circle. To do this, it's only necessary to teach the machine 3 points on the circumference. One high-level command on the teaching keyboard, and the robot should now complete the whole circle. Well, despite its size and power, the robot has to be able to move with a great deal of precision. In this case, it's claimed it can move repeatedly within 1/5 of a millimetre of where it's been programmed to, and that's with 60 kilograms on the end of the arm at full speed. Well, we thought we'd put it to its test. We've put a pin in the end of the arm here. We're going to take an egg. We've programmed it to punch a little hole in the egg, and then it has to whirl around and go back through exactly the same hole. Well, there it is, just one hole. Well, you might ask why anybody would want to use a £35,000 robot to put a pinhole in an egg. Well, the answer's quite straightforward. It's to stop the egg from cracking when you boil it. Until next week, goodbye.